So hello everyone and welcome to this week's Crunch seminar. As every other week, this week too, we have two talks. Our first talk is by Dr. Thomas Lichtenegger. He has completed his diploma and his PhD in theoretical physics and his habilitation in fluid mechanics from Johannes Kepler University, Austria. Currently, he holds the position of a senior scientist in the Department of Particulate Flow Modeling at the Johannes University. His research interest lies in developing computational methods for particulate flow and associated multi-scale problems. Without any further ado, we'd like to welcome you, Dr. Thomas, and you may want to start. Thank you.
Thank you very much. So I'm sharing my screen.
Yeah. Yes.
And, yes, you should be able to see it.
Yes.
Welcome everyone to my presentation about Recurrence CFD. This is a fast data-assisted simulation technique for fluid mechanical problems that involve multiple timescales. Before I begin, I would like to once more thank the organizers of the seminar for having me here. It's really a great chance because I assume that this audience has not heard about Recurrence CFD yet, so I will do my best to advertise it. Thanks to the nice introduction, I don't have to introduce myself, but I'd like to spend a few words on our group. We are the Department of Particulate Flow Modeling. We are located at the Johannes Kepler University in Linz. And since we are a rather small group, we only have a few selected research topics, but they range across the scales. So starting on micro scales, we do some blood flow modeling. It's quite interesting because you have to come up with a good model for each single red blood cell to get the correct overall behavior. On mesoscopic scales, we try to understand the behavior of various granular systems. This means systems consisting of solid particles. They can be very dense and static, but they can also be more dynamic. So depending on what you do to these systems, of course. We try to transfer the understanding or the insights we gain on the mesoscale also to macro scales. So we try to simulate industrial scale reactors, which is where a lot of our funding comes from. We also do our own in-house validation experiments, mainly for the visualization of turbulent flows. So we use particle image velocimetry, where you inject tracer particles into a turbulent flow, and then you use high resolution, high frequency images to reconstruct the trajectories of these tracers, which then gives you information about the velocity field. And finally, this has become more and more important for us over the last few years. We use so-called time extrapolation techniques, where you basically try to generate short high fidelity time series and then make educated guesses about the long-term behavior of a system. And this is also what this talk today will be about. So I will start with the discussion of the limitations we face when we want to carry out numerical simulations for fluid mechanical problems. And this more or less motivates this idea Recurrence CFD. So at this point, I'd like to say a few words of caution. I have, of course, looked at the previous talks in this seminar, which all dealt with very high-level sophisticated machine learning techniques. So if you're expecting the same from this presentation, you will be disappointed. Our method is very simple. It's deliberately constructed that way because this comes with certain advantages, but you will not see any nice deep neural networks or stuff like that. So don't expect to see them. Anyway, we will then proceed to the physical properties of recurrent flows. These are the target systems of our method. And I will show you several application cases. Of course, in the end, we will have conclusions, discuss limitations, and also possible future work. So this slide here is probably a no-brainer for this audience. I don't have to tell you that numerical simulations are important and very useful. They're often called the third pillar of science, where we have theoretical considerations and experiments being the classical two pillars. So basically, if we take the equations governing a system based on theoretical considerations and transform them into numerical code, and we validate this code against experimental findings, this is of course very important to know that it does what it is supposed to do, then we have created a numerical simulation or a numerical experiment inside of our computer. And this is where the usefulness comes from, because we can now just observe something that approximates reality within our computer. We can get a lot of information. We can even play around with the laws of physics. And this, of course, helps to understand various processes. So over the last several years, data have become more and more important, not only for validation purposes, but also for training purposes. They can come either from measurements or from simulations themselves. And we can, of course, use these data to generate better, improved simulations, data-assisted simulations. So I would say, quite independent of the specific problem at hand, one of the greatest challenges that we can face when we carry out numerical simulations are so-called multi-scale problems. In fluid mechanics, one of the most famous examples, I would say, are particulate flows. This means we have solid particles, they interact with each other, they can collide, and they, of course, interact with the surrounding fluid. This could be some gas or some liquid. When we want to describe such a system, we can write down the equations of motion. This is not a big deal, but if we want to solve them, and we have to do this, of course, numerically, we are bound to relatively small particle numbers. So typically, particles are in the range of millimeters or below, but we might want to understand the behavior of an industrial-sized reactor with extensions of tens of meters. This means we have huge numbers of particles and we cannot solve the equations anymore, at least not in reasonable time. And what is more, the characteristic timescale of such systems can be very, very short. For example, the collision duration of solid particles lies usually in the range of microseconds. So if you want to simulate the behavior, you of course have to resolve these short-term processes, but at the same time, this prevents you from going to long durations, like anything that is governed by slow degrees of freedom. So you might want to study a type of chemical conversion that takes place only very, very slowly, but you are bound to these short time steps. And this is, of course, a big problem. So we are in the upper left corner of this figure. This is where we know what to do, but we would like to go to the lower right one, which is much more complicated. There has been quite a lot of research on the spatial multiscale problem, where one tries to understand how one can balance the loss of information one has to accept when one solves the equations of motion on a coarse resolution. So we have a pretty good understanding how to do this, at least for specific problems, but much less has been done on temporal multiscale problem, where we face this massive spread of timescales. So in fluid mechanics, we can usually simulate the behavior of non-trivial flows for a few seconds or at most minutes. But if we would like to go for hours, and this can be necessary in certain circumstances, this is almost impossible. And this is exactly where this new methodology, where Recurrence CFD is located, it tries to go beyond this limitation of timescales. Now, let's have a closer look. Let's be a bit more specific. Why is this a problem? For a particulate flow, we on the one hand side have the fluid problem. This means we need to solve the Navier-Stokes equations, in this case in multiphase formulation. And for each single particle which we want to describe, we need to solve its equation of motion, which is just Newton's second law, but nevertheless we end up with a huge system of ordinary differential equations coupled to the partial differential equations of the fluid problem. All of them have to be solved at the same time, so you can imagine this is numerically very, very tough, and easily the costs accumulate beyond what is reasonable. So in short words, we have a large number of degrees of freedom. This means a large number of particles and a large number of computational cells. We have to take very small time steps because we deal with highly dynamic systems and stiff materials, and this limits us to short observation times. As soon as we would like to investigate the long-term behavior of a dynamic process, we are more or less out of hope. So we indeed need a new methodology, and we need two aspects here. First of all, whatever method should deal with such a problem needs to take into account the spread of timescales. We cannot just use a standard CFD code which completely ignores this problem. Then we are bound by these small time steps, and we can never go to long durations. And what is equally important, since we were, or if we are interested in the long-term behavior of the flow, we clearly have to somehow take a large number of steps, but we need to prevent the accumulation of prediction errors. Or to put it differently, our method should somehow be resilient against such an accumulation. So whatever we do, the method should still work even though inaccuracies might be present. Now to somehow motivate this idea of recurrent CFD, I show you now a few examples from the everyday research work in fluid mechanics. What we see here is a turbulent flow, then there is a bubbly flow. This means a liquid where gas bubbles are rising through the liquid and create various dynamic patterns. And we also see a particulate flow, so basically a box filled with solid particles and gas flowing through them. And what these three examples have in common, if you study them over sufficiently long durations, you will encounter reappearing structures, so-called recurring patterns, characteristic configurations, or sometimes also called coherent structures, which appear again and again. And I'm not talking about periodicity here. This can be a completely irregular reappearance of patterns, but nevertheless, the same structures keep appearing. Of course, these structures, they can undergo some drift over time because system parameters might change slowly, but nevertheless, we can identify them. And this is, of course, important information we can have about the system. If we know that it repeats what it has already done, and we can somehow utilize this information, this will give us a huge advantage. Now, in this talk, I will mainly focus on particulate flows, but there will also be one short example about the turbulent flow. So I would say in our community, the most popular example for a particulate flow is a so-called fluidized bed. You now see an animation of such a case. So we have a box with solid particles, gas flows through from below, and it creates voids inside this particle bed. The voids, they rise, the bed erupts, particles get intermixed, and then the bed collapses again. And basically the same thing is happening again and again. This somehow looks like a bubbling fluid. For this reason, it's also called a bubbling fluidized bed. On the one hand side, this is a very nice test case to understand if you model the physics of the particle-fluid interaction correctly, but this is also important for various industrial cases because there are reactors that operate that way. Anyway, if you have watched this animation, you have probably gotten the feeling that this is very, very repetitive, right? The same thing happens again and again. If we look at these two snapshots of the particle concentration field, they're taken from completely different times. We see that these are very similar configurations. I'm not saying they're identical, but they're very close to each other, even though they are far away in time.
Thomas, what do you mean similar? Because we need to define a norm. Is it in the naked eye norm, or is it in terms of statistics?
Yes, that's a very good question. Because I just wanted to say our intuitive notion is of course not enough. We need to define some kind of distance function. This is what you see here.
Yeah.
So I'm not sure if it's a bad message, but it's an important message. That there is no unique best choice. So you have to come up with some function which you think is reasonable. For example, in the case of a multiphase flow, you might want to compare the volume fraction fields at two different times. You can take the difference and integrate the squared value. If you get a small value out of that, then you can say the flow fields are similar. If you get a very large number, they are dissimilar. But this is, of course, still up to a personal choice what distance function to use. But, well, we have to introduce something which we believe is reasonable. It turns out the final results are not very sensitive towards the choice as long as it's not completely crazy. But I completely agree, we should not just talk about our intuition, what looks similar or what does not. Anyway, once we have defined such a function, we can of course go beyond the simple comparison of two isolated snapshots. We can have a full time series of flow fields and compare each of them with all the others, which then gives rise to such a nice colorful distance plot like you see it here. So basically the coordinates of each point correspond to two different times where we are comparing the system state with itself. This means there is always a main diagonal from the lower left to the upper right corner where we have identical times and zero difference per definition. But of course, what's interesting is what's going on off the diagonal. So if you have a very close look now, there is a highlighted line segment that runs parallel to the main diagonal. This means we have two similar states corresponding to different times, and these states evolve in a similar way for a finite duration. Which is of course what one might expect. If I have two very similar configurations, they should somehow behave similarly. Of course, at some point they will diverge, but for short durations, they will remain close to each other. So this is the type of structure we are looking for in this distance plot, because they tell us about recurring states.
Hello, excuse me, this is Lulu from Japan. I have a small question here. So in the equation here, so why is this a dr to the power 3? Why is 3 here?
I integrate over the volume of the domain. This is just the volume integral.
I see. Okay, it's volume. Okay, got it. Thank you.
Yeah, sure. Okay, so what we also have in these distance plots are structures of horizontal and vertical orientation. These are, and they have a large distance. These are rare events. For example, large-scale eruptions of the bed, which are quite different from all the other configurations which we observe. So these are the main building blocks of such a distance plot. We have these line segments that are parallel to the main diagonal, and we have these horizontal and vertical structures. This type of plot, this has been known in literature for many, many years, and it's very popular to get a more or less intuitive understanding of long-term drifts in the dynamics, for example. But we use them in a quite different way, I would say. So what we try to do is we try to extrapolate the underlying time series in a meaningful way using the information we get from such a plot. So this means, of course, in the first step, we need a high fidelity time series. If this initial time series is already flawed, then the method won't work. So we use some kind of high fidelity CFD technique to generate this initial time series and create the corresponding distance plot. Now in the next step, we march through this series. We have the first flow field, the second, the third, and so on. But at some point, instead of going on, we look what is the most similar configuration in the past. This is just information encoded in this plot, and we continue from there on. So obviously, this depends on the fact that we need to find similar previous configurations, which is just what defines a recurrent system. But if we find such a configuration, we jump back to this previous time step and continue from there on. We take several consecutive steps, and at some point we again look for a previous configuration from which we continue. So this way we can create a sequence of arbitrary length at very, very little numerical costs. And this is all about the data-assisted aspect of the method there is. So basically, this is just an iterated nearest neighbor search or an iterated method of analogs. You can realize this in various ways. We have, for example, implemented it as a Markov process, but again, the final results are rather insensitive how you exactly create this recurrence path. The important thing is that we can get a very cheap long time series that we claim approximates the true evolution of the system. So at this point, you might have a few questions or even angry comments, I would say. You might ask, can such a trivial method be in any way accurate, and why and how should this be useful? Now, I will try to answer the first question right on this slide, and I will use the rest of the presentation for the other two questions. We are talking here about highly dynamic nonlinear systems. This means there is very strong chaotic behavior, and for this reason, we cannot get single trajectories through phase space right. So this is out of question, but hardly any numerical method will be able to do so over long durations. However, if we regard the whole question from a more statistical point of view, things are quite different, I would say. So first of all, we get a smooth time series if our system is recurrent. So if we find sufficiently similar previous configurations, then we create a smooth sequence of flow fields. The next important observation is that each of these flow fields is physically valid if it's regarded by itself. So each of the flow fields has been obtained from a high fidelity simulation, and therefore in our extended time series, when we encounter such a flow field, this might also be present in a high fidelity simulation that would run for a long duration. And what I think is the most important aspect, one can show analytically that the spatially resolved statistical moments of the time extrapolated series, so the mean flow field, the variance, and so on, are the same as those of the short initial time series. So if our short initial time series is long enough to be statistically representative, such that the mean has converged, the variance has converged, then this property carries over to our time extrapolated long time series.
Thomas, I have a question. I have a question here, because of all the flows that you show us
Yes.
are non-Gaussian. So how could you characterize with lower the statistics fields like that? I mean, in fact, if you look at the skewness, it would be different at every point and so on. So just having the first two moments would not be sufficient for inhomogeneous systems.
I'm not exactly sure if I'm getting the question right. So we are looking at spatially resolved time averages.
Right. So the statistics that you're looking at too much are non-Gaussian. Therefore, you need to worry about skewness and intermittency, which is the flatness, the fourth order moments. So just trying to preserve, you can have two different distributions that have the same mean and variance, but they look very different because of the intermittency, which reflects itself on the fourth moment. So how would you deal with that?
So in principle, I would say it's not only the first two leading moments that come out correctly, it's all the statistical moments. Okay. So
sounds like magic. Sounds a little like magic. If I mean,
the
you have to track.
If the short initial time series has already the correct properties, and of course, the higher the moment you look at, the longer it might take to get a converged result. But in the time extrapolation process, you do not change these properties anymore from your initial series.
Okay, thanks.
So, of course, it's a crude approximation, but at least I would say some properties are preserved by this long time series. And what is more, we can, for example, enforce symmetry properties. If we know that our system is reflection invariant, we can augment our initial time series with a mirrored counterpart, which will give us a reflection invariant results in the long term. Now, let me be completely clear. We do not learn anything new about the dynamics here. So this is just basically repeating what we already know. However, it can be very useful, as I'd like to, detail in the rest of the talk, but let me just give a short preview for the other two questions here. First of all, why should this work? It works because it turns out that many systems have this recurrent property. So they show recurring patterns, and they show them with surprisingly short return times. This is of course important because we need to have them in our initial time series. If this would take very long, beyond what we can simulate with classical methods, then this would not work. But it turns out in many application cases, we see these reappearing structures. And we can also somehow deal with transient recurrent conditions where these structures undergo a drift. But this is a big somehow, so you will see about this more later in the talk. Now, finally, when is it useful? And this is connected to the fact that we do not learn anything new about the dynamics. This is useful if we want to construct a dynamic background on which a slow long-term process takes place. So basically, assume we have a very dynamic problem like a turbulent flow, and you would like to study a chemical reaction that takes place only very slowly. So you would like to somehow come up with an approximation to the velocity field of the turbulent flow without having too large computational costs, because you would like to carry the simulation out for a long duration. And this is where recurrence is useful, because you can use this time extrapolation technique for the fast dynamics. You create this background onto which the slow long-term process takes place with hardly any additional costs, and you can completely focus on the long-term process with any numerical method of your liking. So you could use the finite volume method, for example, to study species transport, including reactions, on top of a turbulent velocity field. But let's go a bit more into the details. Let's first have a look at the physics of recurrent systems, which is connected to this observation that we often see recurrent structures. And actually, this is quite a surprise, because you can show that the recurrence time, this means the duration until a pattern on average reappears, scales exponentially with the number of degrees of freedom. So loosely speaking, the more options a system has, how it can evolve, the longer it will take until it has to do something which it has already done. Very loosely speaking, of course, but you can also put this in a more quantitative fashion. So in a typical very small test case of a fluidized bed, we already have tens of thousands or hundreds of thousands of particles. And if we only talk about the particle problem, disregarding any aspects of the fluid flow, and also disregarding any rotational degrees of freedom, we have 6 times the particle number, which constitutes the microscopic degrees of freedom. So we have 3 spatial coordinates, 3 velocity components of each particle. We end up with a huge number of degrees of freedom, and we would end up with a huge recurrence time. So we would never encounter any reappearing structures, which would be very, very bad for our method because it simply would not make any sense. However, in experiments and also in our simulations, on the other hand, we see such recurring structures after very short durations. Now, to solve this puzzle, we had a look at 2 dynamic characteristics of such a system. In particular, we had a look at the so-called correlation sum and the diagonal line length. Both are functions of a parameter, the so-called threshold parameter epsilon, which is kind of a reference distance. So for the correlation sum, we basically count how many pairs of states we find which are more similar than this epsilon. So we are basically looking for recurrent points which have states which are very close to each other, and we contrast this with the total number of pairs of states. So basically the correlation sum is the density of recurrence points and gives us information about the average temporal spacing. So how long does it take until I find a reappearing structure within the accuracy of the threshold value. The diagonal line length provides us with information about the predictability of a system, because it tells us if I have 2 similar configurations, how long will they remain more similar than epsilon. And this allows us to make predictions, because if we have 2 similar configurations and we know how one of them evolves, we can use this information for the other similar configuration up to this prediction time. So the puzzle of the short recurrence times was already solved with the correlation sum. One can show that this quantity has to follow a power law for very low thresholds. This means if we only look at the most similar states, there has to be a very specific shape of the correlation sum. And the exponent in this power law, this is the so-called correlation dimension of the system. You can imagine that the dynamics somehow takes place in a lower dimensional subspace of phase space, and this correlation dimension is more or less the dimension of this subspace where the dynamics really evolves. Now, the important observation is that this correlation dimension, which somehow corresponds to the effective number of degrees of freedom, is much, much lower than the microscopic number of degrees of freedom. So I'm really talking about orders of magnitude here, and because this effective number of degrees of freedom, it is those which are active, is so low, the system actually does not have so many options how it could evolve. So to interpret this in terms of, I don't know, physics, what we see here is a very strong self-organization of such systems. The particle-fluid interaction gives rise to the formation of mesoscopic structures. We have clusters of particles which move together. We have voids in between. So it's not the single particles which would be random walkers that create molecular chaos. We really have organized dynamics, which gives rise to a much more ordered motion with much shorter recurrence times. So this is the reason why we observe recurrent structures, because these systems tend to behave in a surprisingly ordered way. Another nice observation we made concerns the prediction time of the system, because we saw it's orders of magnitude larger than the numerical time step used to generate this data. So this time step is, of course, somehow set by the numerical methods we are using. We want to get accurate results, then the simulations should run stable. This means we have to take small time steps. However, if we already have the data in terms of flow fields and we have 2 similar configurations, prediction times are orders of magnitude larger. And in this case, it's about 4 orders of magnitude. Of course, this depends a bit on the dynamic regime we are in. We see here 2 curves, one for a higher driving velocity and one for a lower one. And if you have more dynamic conditions, prediction times are a bit shorter, but the observation persists. They are much, much larger than the numerical time steps of conventional simulation techniques. And what is important here is spatially resolved information. If we would assess similarity only based on isolated probing points, we would end up with false nearest neighbors. So we would think that configurations are similar which would evolve in completely different directions. However, if we have the spatial information, so if we assess similarity over the whole domain, we do not get these false nearest neighbors. So we only have configurations that evolve in a similar way, and this allows us to make these large step predictions. And finally, one fourth insight, and this is connected to the question we had right in the beginning about the choice of distance function. You can show that for a very, very large class of different distance functions, the final results are equivalent, at least if we only talk about very similar configurations, and these are those which are interesting for us. So we're not interested in very dissimilar states, we only want to know what's happening to the most similar ones. And for those, you really have a lot of freedom to choose your distance function and you will get equivalent results, which is of course a nice message, because if everything would depend on the initial choice of distance function, then this method would not be very useful and would more or less be a random number generator. But based on this insight, one has a certain freedom of choice here and still get reasonable results. So let's make a short intermediate summary. It turns out that driven dissipative systems have often very short recurrence times because they settle down on low-dimensional strange attractors. This means that the dynamics takes place on low-dimensional subspaces with very complicated geometry, with chaotic behavior. And even though the dynamics is complicated on these subspaces, prediction times are much, much larger than the numerical time steps you usually have to use if you want to simulate the behavior of such systems. But of course, this relies on the fact that we have to spatially resolve data to make predictions based on similarity. And if we combine these facts, we end up with this nice time extrapolation method where you get a very, very cheap approximation in terms of numerical costs to the long-term evolution of a system. So what can we do with this? We can model the behavior of continuous phases. We can, for example, solve passive transport equations for concentration fields, where we use the velocity field from our recurrence process. We can also, of course, think about more active conditions. For example, if it's not a passive species, but the energy density of the system, we solve the heat transport equation, which will, of course, change the underlying dynamics. We can also deal with discrete phases, so with a particulate phase. In that case, we can replace the solid interacting particles with non-interacting traces, which just follow the particle velocity field, which has been obtained from time extrapolation. So this is clearly much, much cheaper because no contact detection has to take place, no forces need to be evaluated, non-interacting traces are just moved along field lines. But we can still have any internal properties of our liking. These traces, they can have temperatures, they can have complicated chemical compositions if we want. And this is just where things start to get useful, because these internal properties might evolve very slowly, depending on the local background conditions. And this is just what we can picture with our method. So I'd like to show you now 3 application cases, starting with purely recurrent motion, where the same structures appear and again. This is the most simplest thing you can think of. Then we make our way to transient recurrent behavior, where there is an underlying drift. And finally, there are extremely turbulent conditions where fluctuations basically hide everything. So we have here again the same fluidized bed as you have seen before, but now particles are heated up to 90 centigrade, so they are rather warm, and they are fluidized with cool air. So we would like to understand how fast do the particles cool down. This strongly depends on the dynamics that takes place, because if you have very large gas bubbles that rise through the particle bed, heat transfer will be slower because you have poor contact between gas and particles. If you have many small bubbles, then the contact is much stronger and you will have a faster cooling rate. And this is what we would like to picture. When we computed the
Thomas, did you tell us how this do the CFD in the first place? Is it SPH? What kind of method do you use to generate this?
This is so-called CFDDM, the discrete element method.
Oh, discrete element method. Yeah, I know. Yeah, okay.
Okay, so it's basically similar to molecular dynamic simulations, but with solid macroscopic particles.
Yeah, but yeah, exactly. Yeah. Okay, thank you.
Yeah, so this is a standard method to describe particulate flows. And we generated our initial time series, we computed the distance plot, which looks like this. So we see these recurrent structures. We can hope that our method works. The University of Eindhoven has carried out experiments for this very system. We see here the mean particle temperature over time, starting at these 90 centigrade and then going down towards the temperature of the fluidization gas. The same group has carried out numerical simulations with conventional CFD. This is the green line, which has a bit of a too low cooling rate, but the qualitative behavior is quite okay. So in the first step, we more or less repeated their conventional simulations. We improved certain aspects of the heat transfer, which got us a bit closer to the experiment. But the main question was, of course, how would recurrent CFD perform? And it performed very well. So we basically did not find any discrepancy for the mean particle temperature. However, simulation times for these 10 seconds here went down from about 50 hours to below 10 minutes on the same hardware. So this is really nice. You just start your simulation, you go grab a cup of coffee, and once you return, you have your results. So we also looked at particle temperature distributions. Here we see some discrepancy, but still I would say the agreement between the full CFD-DM calculation and the very fast recurrent CFD simulation, this is very reasonable. And given the huge speed up of the method, I think for most cases, this degree of accuracy is really acceptable. So in the next step, we wanted to challenge the method. We kept on simulating for a full minute. At that time, the particle temperature had almost dropped to the ambient temperature of the fluidization gas. You can imagine getting the reference data here from the full CFD-DM calculation was very time consuming, but we did not find any discrepancy. And let me stress, the time series we used, which we time extrapolated, consisted only of the first 2.5 seconds. So within these 2.5 seconds, the whole dynamics of the system was contained in such a way that we could picture heat transfer for basically arbitrary long durations. What this means, recurrent CFD can be seen as a, I would say, quite efficient way to extract information from short time series. So of course, things get much more complicated if we have transient conditions. Boundary conditions might be time dependent. The slow long-term process might change the properties of the system, so heat transfer will lead to thermal expansion. And it's clear that we won't get away with one single database. So we need multiple databases corresponding to different parameters, and we then somehow have to combine the information between these databases. However, it's not at all clear how to do this. So the interpolation of time series is, to my understanding, not a defined concept at all. You cannot just take two time series and get something in between. Then whatever we do, we want to get physically valid flow fields, and this should come at little numerical costs. Otherwise, we would lose any advantage we have gained. And these are, of course, quite heavy demands we have here. And I have to admit, we have not found a really good solution yet. We have some solution which works to some extent, which I will explain now, but this is really crude. Now, assume we have two time series for two distinct dynamic regimes, for example, a low velocity case and a high velocity case. And we can combine them into such a combined distance plot. So the lower left and the upper right quadrant are just the distance plots for each time series by themselves. And the off-diagonal blocks are the similarity matrices between the low and the high velocity case. So what we can do is we start our, or let me put it differently. We would like to picture the conditions somewhere in between these two extreme cases. So, and to somehow characterize this in-between condition, we may assign weights to the extreme databases. So we might want to picture something which is exactly in between. Then we might have equal weights for both databases. Or we might want to picture conditions which are closer to one of the regimes. Then of course this weight would be larger. Anyway, we start with our recurrence process as before. We take these several consecutive steps. We go to a similar previous configuration and continue from there on. But at some point, we make a transition to the other database. So we continue from there on. We take several consecutive steps in the other database. And at some point, we will make our way back to the previous database. The idea is to have intervals of consecutive flow fields where one interval is taken from one dynamic regime and the next interval might be taken from the other dynamic regime. And ideally, the total fraction of time spent in each of these databases would correspond to the previously defined weights. So on a temporal average, the resulting flow field might look more or less reasonable. But of course, if I just look in instantaneous flow fields, it's either one from the low velocity or from the high velocity case. So I never have a correct state I'm using, but on average, hopefully these errors I'm making average out. The advantage is it's numerically equally cheap as the initial method. The downside is I'm always making some kind of prediction error. So let's have a look how this works. It's a similar case as we had before, a fluidized bed simulated with CFD-DM. Now the particles have internal heat sources. This means they produce heat. This mimics an exothermic chemical reaction. And for this reason, there will be a dynamic equilibrium for the mean particle temperature. This means the higher the gas inlet velocity, the more heat we will take away from the particles, and the lower the dynamic equilibrium value will be. But such a dynamic equilibrium will develop depending on the gas flow rate. So we start with a low inlet velocity, and then after 300 seconds, we ramp it up to a higher value, and then we keep it fixed for another 200 seconds. So this is where the requirement to interpolate between time series comes in, because we only have a time series for the low velocity and one for the high velocity, but we would like to understand how the effect of increasing the inlet velocity, how this takes place. So this is the mean particle temperature over time, and before I walk you through this plot in more detail, the main observation we can make is that the mean particle temperature from recurrent CFD, which is the red curve, and from CFD-DM, which is the blue dashed curve, they're almost identical. So it looks like the method works. For the first 300 seconds, we have the constant low inlet velocity. So this is almost the same problem as we had before. We already know that the methodology works in such cases. This was not a big surprise. Now, what was more of a surprise were the next 300 seconds where the inlet velocity linearly increased. So we jumped between the databases. First, most of the recurrence path was spent in the low velocity database, and only some additional fields were added from the high velocity database. But over time this changed, and we added more and more contributions from the high velocity database until the whole approximation took place in that one. And it turns out for the mean particle temperature, this was completely okay. It's a crude approximation, but if we are only interested in this property, then the approximation was fine enough. For the last 200 seconds, again, no big surprise, a constant high inlet velocity, just one database was used. The results agreed very well. Now, only if we looked at the temperature distribution of the particles, or rather its width, we did find some discrepancy. And this is, of course, located in this transition region where the inlet velocity changed. So for this time between 300 and 600 seconds, we see that recurrent CFD produced very strong fluctuations for the width of the temperature distribution. And the reason is that the width immediately adapts to the current database. So if we are in the low velocity database, the width is larger. And as soon as we switch to the other database, it gets lower. And this adapts very, very quickly. If one knows how to interpret this result in a statistical sense, one can, of course, filter this curve. This gives then this green dashed curve, which is very close to the CFD-DM result. But this is more or less proof that the method is a crude approximation when we try to picture intermediate conditions, and well, it only works somehow. Now, the last example, and I won't go into so many details here because, well, time is limited, of course. Here we have a submerged jet under turbulent conditions. So liquid enters a box with high velocity, and this liquid carries bubbles. What will happen, the liquid can exit the box through the bottom, and the bubbles will rise through the top through which they exit. What we would like to understand is, how does the long-term distribution of bubbles in the domain look like? How far into the box can these bubbles penetrate? Which is important, for example, in certain steel-making applications where liquid steel is treated that way with argon bubbles. If we look at an animation of this jet we see that it's extremely unsteady. We have many fluctuations, and even though we can somehow identify larger scale recirculation areas, everything is very noisy, right? And this reflects in the distance plot we have computed. We more or less do not see any off-diagonal structures. There is no similarity between states over the whole domain because there is so much noise. And well, this sounded like a very bad message for us. If we don't find similar states, how can we make predictions? So to our big surprise, if we just applied the methodology, the results were not that bad after all. On the left-hand side, we see here a large eddy simulation, the ground truth for our case. And on the right-hand side, we see the result of recurrence CFD for the time averaged bubble distribution in the domain. And we see there is not so much difference between these two results. If we go to higher velocities, of course, we find some differences, but the qualitative behavior, I would say, is very similar. So for this high velocity, some bubbles are entrained and move downwards, which we observe in both cases. Also, if we look at the total number of bubbles in the domain, so-called bubble holdup, we have a very good agreement for both the low and the high inlet velocity case. In both cases, recurrence CFD and the large eddy result agree quite nicely. Now, why is this the case? It turns out this property that the statistical moments of the time extrapolated series are the same as those of the initial one, this persists. And if your long-term process you're interested in is not too sensitive against abrupt variations, then this can still work. Because now, of course, we have very abrupt variations. We do not find similar configurations from which we can continue. So we have to continue from any previous configuration. We have strong variations. And if you are interested, let's say, in a diffusion-driven process, this might be a problem. But in this case, just for simple bubble transport, it turned out that, well, the method even worked without the identification of really similar states. So I'm now skipping this slide because I'd also like to spend some time on the concluding remarks. I'm also skipping the discussion of related work. I'd just like to mention several people have contributed to this methodology. In the beginning, it was only our group, but by now a few other groups are also picking up the method, which is of course nice to see when others start using your work. But still our group is the main host of the method. Anyway, the main conclusion I would say is that we can often observe recurrent structures in driven dissipative systems if we study them over sufficiently long durations. And this is important information we can have because we can now make large step predictions based on similarity. So we need the data, we need the spatially resolved data, but once we have it and we can identify similar structures, we may use this observation and make predictions with very large time steps. So of course, this does not tell you anything new about the dynamics of the system. You only have the information contained within your short initial time series, and you cannot generate new information out of that, but you can generate a long-term background, a dynamic background on which you may study long-term processes. So this is where the method is useful if there is such a long-term process which you would like to study and which really depends how the dynamic background looks like. You can use any conventional numerical technique of your liking to study this long-term process and, well, save a lot of computational time. Now, clearly our method is very, very simple. There's no discussion about that, but I think this comes with advantages. We have very large speedups between 2 and 4 orders of magnitude compared to the underlying CFD codes. This is really nice. Of course, we have this one-time effort to generate the initial data, but once we have this, there is no training involved. The method is numerically stable because we actually do not calculate anything for the approximation of the fast degrees of freedom. We just take the existing data. And due to the simplicity, we can also generalize easily to other cases. I would say there are 2 major limitations we are facing. First of all, if we go to very large system sizes, the number of effective degrees of freedom increases and therefore the recurrence time increases strongly. This means when we want to simulate large-scale flows, we have to either extract the most dominant degrees of freedom or make predictions in another way, going away from this system-wide similarity. And the other large limitation are changing flow conditions, where we now jump between the databases, but this is extremely crude, of course, And as soon as we have strong coupling where the long-term process really influences the dynamics that evolves, then this will not be accurate enough. Just one point, which is, I think, beyond our methodology: rare events, if we do not see them in the short initial time series, we won't see them in the time extrapolation. Now, before I come to the end of my talk, there are two short ideas I'd like to share with this audience for very practical reasons, because I think I could get some valuable feedback. The first idea concerns how we make predictions. So far, we looked for states which are similar over the whole domain. But from a physics point of view, I would say if I want to study the evolution at a certain specific point, only the extended neighborhood will contribute. There will be some kind of radius of influence, and everything which is within this radius will somehow contribute, and everything which is farther away should not play a role up to a certain prediction time. So if I want to make a prediction for a point, I only have to look for states which are similar up to this radius of influence around this reference point. Or at this point, it might be feasible to train a neural network which takes as an input the local flow conditions of this subdomain and is trained to make a prediction how the flow at this point will evolve. I can do this, of course, for every point in my domain and get a new flow field a large time step later. However, the large problem I'm facing, if I make a prediction for each point independently, there is no way to guarantee that I get the correct spatial structure of the flow at the next time step. And as soon as I would like to make another prediction step, this will be a large problem because spatially resolved information has turned out to be very important. So I don't know how I could check if the spatial structure of the flow is correct because it's not directly encoded in the laws of physics. Of course, I can check if the divergence of a single phase flow vanishes, but there is more to the spatial structure. And this is where I'm stuck for this method, how I could incorporate or how I could check if the spatial structure is correct. The other idea I'd like to share, and I know I'm approaching the end of my talk, so it's just one more slide, is about if we can create intermediate time series with little numerical costs. So assume we have two high fidelity time series for very different conditions, and we can, of course, compute statistical moments up to whatever order we want from, or which we can reliably do from these short time series. We can compute correlation functions. And maybe we can make educated guesses about these statistical moments at intermediate conditions. So this is something where we really might try to use just arithmetic or weighted means, which is of course not possible for the time series themselves. Now the question is, and here I have one neural network on my slides, would it be possible to use a physics-informed neural network, tell it how the mean flow and the variance and whatever information we want to pass to it should look like? We also have, of course, the boundary conditions and the laws of physics, but nothing else. And now the question is, would it be numerically sufficiently cheap to train a network with this information to generate time series at intermediate conditions? If I could do so, if I could generate a large number of different time series for slightly different conditions, this would immediately solve my problem of transient behavior, because I could just generate such a time series whenever I needed it. It need not be long, because I can then again time extrapolate it with the existing recurrent CFD method, but I need some way to generate a time series if I make an educated guess how its statistical moments should look like. So with this, I'm really at the end of my talk. I hope I was able to spark some interest in you for this methodology. I would be really happy to hear any feedback if you have any questions about the method, or if you have any feedback with regard to these ideas for future work. I'd be really happy to hear them. Anyway, thank you for your attention.
Thank you, Dr. Thomas. Do we have questions for him?
Thomas, about the maybe having a DeepONet, physics-informed DeepONet may be better, perhaps, for this type of learning. Mm-hmm. Don't know if you have looked up the physics-informed DeepONet, but it corresponds to different types of conditions. But recurrent networks also, but DeepONet can play that role of the recurrent neural network. But I agree with you that some sort of a approximation like that, and I worked with Johannes Kepler University before, who did the equation-free method for this fluidized beds, and he would go burst of DNS, go back to extrapolation with like let's say POD basis and so on. That's a cheaper version. But in all this, my question is, how do we know how big of a crime we commit? Because if we don't know the answer, so you will be very happy, but you may have killed the physics, and that's the problem that I'm saying. We commit a crime, but we don't know that. So if there is a measure, like in pins, for example, we monitor the residuals, and we know how bad or good we're doing. In standard CFD, here, what is needed, I think, is a metric that will tell us, look, you're really committing a big crime.
Yeah, that's. Thank you for the feedback. I completely agree. It's a bit difficult here to estimate how large the error we are making is. So typically we try to, or I would say the longer the initial time series, the more reliable the information we have. So one thing we do is we look at the statistical moments if they converge, because if, for example, the initial time series is too short to have a converged mean flow field, then this will be an error that carries on. The other way to do is to compute properties of the distance plot and see if they are converged. So basically you can check if how much new information would be added if you continue your time series. And at some point one finds out that this levels off. So if you would add, or if you had a longer time series, you would not have more information within your distance plot in terms of dynamic properties like the correlation sum, for example. And at this point, we usually say, okay, the time series is long enough to represent the flow in a reasonable way. But of course, there is no strict metric that can somehow tell us how inaccurate the approximation is or how large the errors are. So we can just try to compare with a detailed simulation that we let run for longer times and see if there is any difference between the results. But this is of course limited because these detailed simulations cannot be carried out for such long durations.
Right, right. Then in about these correlations in space, in geospatial statistics, I think there is something, it's like Gauss random fields, but with a Markovian property in space, not in time. Do you know this type of methods? It was developed by Russians, and I think there was a significant paper that was presented by some Swedish people in the Royal Society of Statistics, say maybe 10 years back or something like that, and was used in we kind of worked on that with my PhD student Paris Perdicaris, who is also now, and then he moved to pins, but before that he looked at that this type of I could offline send you that paper because it could
this would be very nice. I haven't thought about this approach, but this would be
so this is used in statistics, but these people they use it in climate, they use it many different to scale up the system, like SS surface temperature of the entire globe. They have a lot of in arbitrary manifolds also, but I think that correlation in space that you described, that could be captured nicely with this type of, which are large scale, but it's basically the Markovian property in space, not in time. And there's a way to check that you actually have that property.
This sounds very useful, yes. So it would be really nice if you could send me this paper.
Yeah, okay.
If we have no more questions, let's thank our speaker. And thank you, Dr. Thomas, for tuning in and giving us this wonderful presentation.
Thank you for the opportunity.
We'll move on to our next speaker, Qian.
Hi.
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 Yeah. Can you try sharing your screen? I made you the co-host.
You didn't give me the permission. Okay, now I have it. Thank you.
So our next talk is by Qian Zhang. He would be talking to us about solving quantitative reasoning problems by language models, and he's a first-year PhD candidate at the Crunch seminar.
Thank you. Can you see the PPT here, or you see the entire slideshow mode, or end with my comments?
Yes, we see everything. Like
All
your
right,
and we see 2 slides. So
okay, so is this fine now?
Yes, but again we see.
Oh yeah,
this is
okay.
fine. Yeah.
Okay, thank you. Today I'd like to introduce something very interesting from Google research. They have trained a huge language model to solving quantitative reasoning problems. Well, it seems to be a very fancy name, but actually they're trying to use NLP models to solve math and physics problems, and they have achieved some success. Well, in the high school and the middle school STEM problems, and let's see what would happen with this interesting research. Let's just review the background of this research stuff. The first thing is that nowadays deep learning has achieved very great success in the NLP area. Well, the famous GPT-3, they can do copywriting, summarization, text classification, and translation stuff. And just the year before, OpenAI has just created something called DALL-E. They can create images just from the text, like a painter. And now it's a very controversial news that someone at Google claimed to say that so-called Lambda, NLP model, they have to be sentient. Of course, this is something very controversial, and most people think that this engineer simply loses his mind. But still says that nowadays NLP models are of very high intelligence that can, to some extent, fool the people. Well, the common points of this research is that they all use tremendously large neural network, which means they have billions of parameters and possibly trained and inferred on the CPU stuff. And of course, these are not only the good stuff about this research, they have something struggling with the quantitative reasoning. That is, they can actually take in the words and give you some results, but nobody can guarantee that they are actually reasoning. That is, infer step by step. They seem to take something in and give you something out, but they can't see the logics between the input and output. So that's an interesting problem here. And this research on solving the quantitative reasoning problems with language models aims to deal with such problem. That is, they want to use certain data set with some other techniques to find a good way deal with the quantitative reasoning, that is, provide the neural networks the ability to reason step by step to solve STEM problems. Now let's just start from something fascinating and let's get some confidence about this stuff. First is the text summarization. That is, when you input an article to the neural network, and it will summarize some sentences to show that the main topic of this stuff. Well, just imagine that you can, when you get some paper to review, you throw the paper into the neural network, and it will tell you that what they have done. It will save you a lot of time, of course, but just a simple case. You may use this later in GPT-3 to find whether it works. Another thing is from DALL-E, that is, they can create fascinating images just from the text you input to it. Like these 3 images, they all are plotted by the computers with single sentence that an astronaut riding a horse, or in the photorealistic style. Or they paint the images just from their models. It's very interesting stuff. It seems that now we can hire our own painter and do not require to pay a lot of money to reach these students. And another thing is the Lambda thing. It may be a little abstract, but this is the conversation between the Google engineer and the Lambda chatbot. And you can see that it gives you some very philosophical sentences and kinds of deceive the people to make them think that it has some sort of sentience or emotion, or it's self-sentient ideas. But we're just providing this stuff to show that actually NLP models has a very strong ability to create a lot of interesting things. And now let's test it with something familiar to us, but not necessarily familiar to them. That is a STEM problem. Well, the problem here is quite simple. That is, well, let's just starting from point A in this stuff. And A here, he will choose 4 possible directions. Each time she will choose, when he comes to intersection, she will again randomly choose one of the possible directions. And the question is, what's the probability that in the first 4 steps, he will move around the gray square? Oh, that's quite straightforward. You just have the power of 1/4. So that's it. But of course, you need to time 2 because there are 2 clockwise or counterclockwise. But this is the generated solution from former language models. If you throw the problem in, they will give you something totally unreasonable. So this is why the Google guy is trying to develop such a language model that trained it to deal with the problem in a very reasoning way, that is step by step via the logic inference. And now they created something called Minerva, the wisdom goddess in the Roman tales, and of course they hope to be something as clever as the goddess, so that's why they name it. The model detail is first, it is based on the very recent language model called PaLM, Pathways Language Model, also developed by Google. And it has 8 billion, this is 3 versions actually, 8 billion, 62 billion, and 540 billion parameters for each model. And just notice the unit, it's billion. And they are trained with V4 TPU on Google Cloud. For each of the 3 versions, they use 14 days, 17 days, and the longest ones, of course, the most expensive ones, is about almost a month. And also they are using a tremendously large training data set. That is, they're using 1.2 million archive papers, totaling 58 GB of data. Just imagine 1.2 million archive papers. I guess nobody here can read so many papers in life. And of course, they also use approximately 60 gigabytes of the mathematical web pages, just like, imagine the mass Stack Overflow or something like that. They use all these stuff to train a model that can give you the output like this. It seems to be, have the ability to infer step-by-step in logic that is quantitative reasoning. So the first is they are trying to, it's kind of like statistics problems, and they're trying to compute on from the information given you, and they're trying to get the results. Another is proof and very fundamental inequality. And these 2 steps shown, if you check them step by step, you will see that each step is correct. And of course, the result is correct. And even they can do more than just math. They can do physics as well. So here is an interesting example that a uniform solid disk starts from the wrist and rolls down, applying without slipping. And they ask on the fraction of disk's total kinetic energy. And
Hi, Qian. I have one question. So for example, for the previous page.
Yes.
So I assume the right question in the right figure here definitely is in the training data set, right? If they have all these web pages, then I assume this should be in some web page of the existing web page. This is in the training data set.
I guess so as well.
How do they check whether the problem is used in the training or it's a new problem, or they didn't check it?
Actually, I think in their paper, in some details, they have talked about it, but I didn't put into the show.
Okay.
If you're interested, I can show later check their original paper and see what they are using. And actually, they have some out of training data sets. They have some other evaluation data sets as well. And then later on, we can see what would happen.
Qian, I think they have a version of the model is free for a short time, right? When I was reading this blog, when I gave you this, the guy got hold of the model for free, and he was able to do his own experiments. But then you have to pay after a while.
Really? I'm not quite sure about this. Google, it's a quite recent paper. I don't remember.
I think it's free there's a way to get hold of it for free for just a short time, maybe a week or so. I think
Okay,
a week, yeah.
Yeah. Okay, so yes, then, well, an in-sample, all-sample problem is a good question, and I will check this later. This example shown that they can also deal with the physics stuff, and they can even do something more than just arithmetic computations. They can take derivative, and well, all this derivative stuff is very simple derivatives. And here is the results, and you see the computation here is well, reasonable. I mean, in the logic step actually. And now I will come to the details of this so-called Minerva model, and they using 3 kinds of different data set to do the model evaluation. Well, the first 2 are just from high school, middle school math problems, which is quite simple. The second one is a little bit advanced that use the MMLU, that the multi-task language understanding, and they use the STEM subset of it. It will ask some STEM questions, not necessarily just the math problems. The last one is the most advanced data set they used in their evaluation thing. That is the MIT OCW data set. OCW is MIT's open course web page, and it includes the undergraduate level STEM problems. And they want to show that this model can answer on almost 1/3 of these problems, and it shows the good ability in quantitative reasoning. Is their accuracy, and well, they have the legend here. The POM 8 billion is the, well, POM 62, POM 540 are just the most plain model that doesn't use their data set to well, let's see. Yeah, this is what they used to fine-tune the POM data set actually. So here, these 3, POM 8B, POM 62B, POM 540 billion, are not trained with their mass data set. And for the Minerva, they used to train the data set. And here, the majority 1 at K as their way of evaluation. This is an interesting technique, and we'll explain this later. And just from
Qian,
this, yes?
Can I ask, please, how do they measure the accuracy? Like, there's I don't know, a TA that actually grades their.
It sounds like well, if there's 100 problems, you have correctly answered 8 of them or 80 of them, then you have 80 in the accuracy. This is,
so they just checked if, like, they looked at the answers of the model and like tried to see if the question is answered correctly.
Yes, because
Wow.
most of these questions are multiple choices, so it's quite easy to do the stuff. And for some, well, other things, or they have also discussed the false positives. I will discuss this later as well. So some other questions are, well, just like they output a single number or some very easy polynomials, so it's quite easy for them to check the accuracy as well. So you don't need to necessarily to compare them by hand.
Hire someone to grade a robots
well, they
exam.
did hire someone to create a data set, but they didn't hire someone to grade it.
Yeah.
Yes. Yeah.
Cool,
so welcome. And you see here, they are when they use larger models, when they use more complicated techniques to do the evaluation, they have better accuracy on it. And if we just focus on the MMLU stuff, we will need to we can actually compute the average of the performance on these overall stuff, and this is actually a very large number. Let's see it. This is the MMLU performance till May this year. And for the STEM things, just see the STEM column. Even the most advanced model in the May, it's named Chinchilla. It only achieved about 55%. But here you see their overall performance, if they use the Minerva, the largest Minerva model, they achieve more than 70. So this is something really great improvement in the stuff, and they are targeted quantitative reasoning. So I not compare this on other, well, subjects or fields. So they claimed to be a great success, and let's dig into it and see what happened. So, well, the numbers here, since this is a plot, the numbers here shows that when they use larger and larger models, you can achieve actually, well, just higher results, higher accuracy in the results here. And the majority 1 at k is actually, well, let's say that when the model gives you an answer, it does not only answer the question only once. They require the model to provide you, for instance, like they ask the model to compute the same problems for 20 times. And they actually want to find the most common pattern among the 20 times. For instance, if this is a multiple choice problem and the model answered the same question for 20 times, if the 12 of these times are the model are choosing B and all the other times that they're just choosing A, C, or D stuff, then it will use the B for the output of the model. They are using this technique depending on the very heuristic instinct that when you do something wrong, there are a lot of ways to do something wrong. But when you do something correct, there's only one way to do something correct. So they use this heuristic stuff to create a technique called majority 1/k. And you see it has improved the performance with same parameters numbers. Well, actually a lot, over 10% in most of the cases. So this is something very interesting. And they, as you can see here, they achieved on the MMLU STEM stuff, they achieved 75. This is far higher than the current for SOTA model on the, well, MMLU STEM set. And of course,
excuse me, Qian. This
yes?
is Panos Tinis. I have a quick question.
Yes, please.
So what is random about this model so that if you query it multiple times, it will give you different answers?
Yes.
Where does the randomness in the answer come from?
Well, this is the randomness lies in the well, language model, because it's a transformer stuff. When you try to input tokens into it, it will not necessarily give you the same answer.
So it's not a deterministic model that
it's not deterministic. You're right.
Right. So do we know in the transformer where does the randomness come from? In which, point in the model there is this randomness that is injected? Because I thought that they were deterministic, that I give it an input and it will always give me the same answer.
Well, I don't know about it. POM is a really large model. I didn't dig into the details of the this thing. I will check this later.
Okay. All right.
Thank you very much.
Yeah.
Yeah, and well, just as Panos says, it's not a deterministic model, so this is why their majority 1/k stuff can work, and it shows an improvement. And now we need to discuss something on just draw the interest of Panos and Adar before. That is, the model in the model evaluation, did it really learn to reason, or just they are getting lucky? The first stuff is false positive. That means you have a correct answer, but your reasoning is totally wrong. Just like, well, when you do some multiple choices, you don't know the answer, what it is. You may just guess a C here. And if you're fortunate, then that's the right, that's C. But when you try to write the steps, you're totally wrong. So this is important thing here. They try to figure out the false positive rate. Here, just like Adar says, they do hire people to take some output and manually grade it to see if this is the correct answer with correct steps, or they just have a good luck with totally wrong steps, but with good correct answer. So they find hundreds of problems, divide them into different levels, and compute the false positive rate. And they finally get a result of 8% of the false positive rate. That is, they just guess the correct answer, not they are doing it. And this, well, the difficulty level from 1 to 5, 1 the simplest, 5 is the most difficult part. and also corresponds to the false positive rate. When the problem is much more difficult, you are tending to do the guess stuff. Otherwise, you cannot have an answer. So this also makes sense. Another thing is the memorization. That is something called rote learning. You just remember it and you don't know what happened. This thing may happen because when the input data, for instance, it is a number like, let's think a problem. They say that, okay, 1 + 2 = 3. Now, when the model see 1 + 2, it will give you 3, of course. But what happened when it comes to 2 + 5? So if the model didn't learn the sense of the additivity, then it may get you some wrong results. And here is the plot of the how they try to inspect how much memorization stuff happened. And this plot is the original thing. That is when the modified framing means they just rephrase the problem. It doesn't change the number or the logic of the problem. And you see on original, when higher the original accuracy is, they also get higher accuracy in the modified problem. That means whether rephrase or not, the original problem doesn't affect the accuracy of the model. So they have a good robustness against the rephrasing. And the next plot is of modified numbers. That's just like I said, if you from 1 + 2 to 2 + 5, then what would happen? It seems that there is a little degrading the model's performance, but still they are positively related, and the higher original accuracy will lead to higher modified accuracy. And this is the majority voting accuracy. That means when you have a good, this blue score measures the similarity between the two sentences. So when the sentence, the input problem, the modified input problem is similar to the original modified problem, then the accuracy will saturate very quickly. That means that means even if the similarity between the two problems are not so high, it's still maintaining a good accuracy. So this is evidence that the model did learn some reasoning techniques, not just remember a mapping between the input to the output.
So
Yes,
for the
please.
middle figure, for the modified number, it seems to me the correlation are pretty weak.
Yes, exactly. But they still claim that this is the correlation here. So what they say in the paper is, yeah.
Okay.
Yeah, so this is a very new paper, so it still may be controversial in many aspects. And for me, I also think that this part is not a strong correlation thing. Now we go to some final example about these models. The first thing is this is evidence that a larger model with more parameters can outperform the small models. The 62-bit, just to review the question, from these numbers, they draw and replace with replacement and compute the probability with n times m = 24. And the 62 billion model, they say, okay, I have all these possible pairs of numbers. And they say, only pair that satisfies this equation is this. Of course, this is totally wrong. You can find like 3 × 8. And this is what actually the 540 billion model says. They can have all these possible options and the total cases. So the probability is this one. So here we see a larger model can learn stronger inference ability from the questions. But still, the model here doesn't necessarily always give you the correct answer, even if it's using the majority when it overcame the technique here. First top choice of the model output is 540 billion. Both of them are the largest models. Well, the top choice is actually not correct, while the second is correct. Here is the GCE. It is an exam in the Britain and sort of like evaluation of the math ability for high school students. So it's still a high school level problem, doesn't include advanced stuff, just like calculus. And even for these simple problems, model may fail. Of course, it can give you some correct answer, but they are no longer the top choice. And the third case is a totally wrong stuff about the model, even if it is the 540 billion parameters. This is from the JEE main exam. It's I think it is an Indian national examination for the technology school admission. So you see here, there are some more tough cases like limitation of the certain polynomials, or sorry, not polynomials, it's a certain thing. And well, it seems to have some intelligence to, just try to find and cancel some terms, but it will give you something totally wrong. It did not make only one mistake here. From this to this, from this to this, they all made some problems. And and this shows that the Minerva model is not so close to the people. Actually, it's far below the people performance. And you see, even if it can do some STEM problems, it can do can get 1/3 accuracy on the MIT OCW dataset. It doesn't guarantee that it can do everything correct, even on some simple cases, and it will just fail on some difficult cases. Now, I try to summarize the contributions and the limitations of this paper. This paper claims to have the largest contribution of this paper is a very large training data set that use the natural language with the correct use of formal mathematical language. Well, it's unlike the former data set used by Google or other companies that only emphasize what they sample from Twitter or sample from other social media. This data set focus on the STEM stuff that has the logics, that quantitative reasoning with numbers. They need to compute and analyze in a scientific way. So this data set is very hard to obtain. They did a lot of things to clean the data set to ensure that the data set is of much information. And next, their contributions, they can show that by training a very large language model on this high quality mathematical data set, they can achieve a strong performance on these tasks that require logical reasoning, even some numerical calculation and symbolic manipulation. But still, there are some limitations for this one. The first is there is no such automatic way of verifying the correctness of the model's answers. Even if for the multiple choice problem, they can give you some answers, but you don't know if it's really correct or they just have a good luck in the guess. So you still need to take out certain problems and sample from the answers and do it, grade it by some people they hired. And of course, there's another thing here is that they have no access to external tools, just like Python interpreter or calculator. Because if you have the Python interpreter, it can formulate, let's say, if they have a Python calculator, they can just parse this expression and send it to the Python interpreter, which has a SymPy, and then all this stuff will not. That would be quite simple because the SymPy things have a good ability to do the computer algebra thing. And the last thing is, still well below the human performance, because as the matrix says, on the MIT OCW dataset achieves only 1/3. Let's say an MIT OCW 100% will let you become a very good undergraduate student, achieving only 1/3. It's still hard to make someone to graduate, to obtain their bachelor's degree with such accuracy. So let's say this model seems to be very interesting and shows a promising way in the future. But for now, it's still not quite hard to become a good and a reliable research assistant. So here is the summary of the large language model. The first thing is the larger, the better. As just said before, the Minerva model with 540 billion parameters has very good performance over the smaller two. The second part important is high quality data sets is very essential to such research because, well, if you have some data set from Twitter or from social medias, you cannot expect it to have the quantitative reasoning ability because they're in their data set, they don't have such ability. The data is the most important part for such kind of research, and Google has hired a lot of people to do create such a good data set. And finally, to achieve the first two, you need to be very rich because when the large data sets, you need to, well, hire a lot of people to do annotation, cleaning, and something else. If you want to train a larger model, you need to buy the TPUs from Google, and that can cost enormous. But after all, language models for now has shown very promising future, and we may able to sometime we may able to find the very powerful language model that can help each researcher in their specific problems. And that in that time, I think that most of our researchers have an easier life. That's of course a good future, and I hope this one is a good hope to you. Thank you very much.
Thank you, Qian. That was wonderful. Do we have questions for Qian? George.
This was, so do they mention that they can have access to a calculator in the future?
Well,
a lot of those, just a basic calculator?
They just say it doesn't have the access to calculator for now. They didn't mention whether to have the calculator for future, but in their appendix, I did see how they transfer they parse their input, their some source of output to the code. So I guess in the future they will use the external tools like interpolator or other calculators.
Yeah, or they can download handbooks and so on, right? They
yes,
can,
yes.
Like I said, say for. But I was about this subhuman performance. Even with 540 billion parameters, they're less than 10 to the 12 parameters, right? That's less than terabyte. So that's less than by 3 orders of magnitude, at least 3 orders of magnitude, less than the number. So we have 10 to the 15 synapses approximately. So that will be the number of parameters that Hinton is talking about. So obviously the number of parameters in that model is lower by at least 3 orders of magnitude of the human number of synapses.
Yes.
So you don't expect miracles, right? Even
yes.
But I thought that's why I suggest that you do this. It's a first model that integrates mathematics and physics into a language model with the reasoning. So I thought it's really interesting that
yes,
it
exactly.
could potentially change the paradigm as I think the Chinese. What is the name of the Chinese? Not Wally. What's the name of the Wudong? What's the Chinese Academy of Science big language model, which is close to 1 trillion parameters?
I don't really remember.
Yeah, I think that could go closer if they add if they add math from all the Chinese universities. I think that's lots of data there. Yeah.
I have a question. So when they say that they read the archive papers, what do they actually do? I mean, what do they explain? In what sense do they read the papers? Do they look at the formulas, the text, the discussion, the abstract?
Yes, this is a very interesting question. They're quite an important technical problem. What they do is they, for instance, they have downloaded an archive paper. They will parse from the PDF to get different parts of the entire text. For instance, for the abstract, they will start with a chapter named abstract, and there are some sentences after it, and therefore there will be another chapter, for instance, introduction with some sentences. And when it comes to formulas, it will parse the formulas into the text expression, just like how we write LaTeX on relief or something like that. So what they do is to transfer a PDF file into a pure text file, and then split the pure text file into tokens, and then feed the tokens into their language model.
Okay. And in these 1 million archive papers, I expect about, I don't know, half of them to have errors there in the formulas. So all I'm saying is that because you mentioned high quality data sets, how much, we don't know how much error we're actually introducing in the education of Minerva, right?
Yes, yes.
Hopefully not too much.
I hope so.
Yeah.
Well,
Yeah.
they do need a very huge data set. So on the most accessible to Google, there are only, well, the first choice is they use the spider to get to the internet and capture all the data, all the web page with the nodes like /math, so they can copy it down. Another centralized stuff is the archive, because it's so many mathematical or physics paper on it. So they do not have so many choices, and
Right.
then these two may be the easiest for Google.
Yeah, but I heard or read the statistics about math journals, but that was many years ago, that I don't know how they estimated, but they said that about 20% of the theorems that are published each year in math journals are wrong.
Oh,
it's just that the peer review process is not the best anymore, and somehow they pass through. So you can imagine what will happen if they start reading math journals, right?
yes.
I mean, this thing may get a very skewed idea of what is correct.
Yes, you're right.
Yeah.
Possibly they
Yeah.
will just learn some forced computations from
Yeah.
the archive thing. But this is a large language model, so Google themselves says that it's hard to investigate into the details of the model.
Right. Of course. Yeah. Yeah.
I want to comment on that 1.2 million archive papers in the archive. 4 years ago, I was attending a workshop at DARPA where they show this cancer pathway. It was a very complicated pathway. So they asked who can you guess which group came up with this pathway? They said, Stanford, Harvard, Johns Hopkins, and so on. He said, no, this is a computer. And this computer read 100,000 papers on oncology. And that was considered state of the art, 100,000 papers on one topic, oncology, 4 years ago. So now 1.2 million papers all across mathematics and physics. That's pretty amazing on its own. So, it's a leap.
Yes.
It's a huge jump. Yeah.
Yeah.
Kamal, you wanted to ask some question. You just switched on your video for some time ago.
I just saw a similar video in YouTube actually, and YouTuber got access to the I think library and the code. The initial the photo generation model actually.
It may be how the model has the access to external tools.
No, he got the access to the Google model, and he was generating some picture from the text actually.
Oh.
So YouTube one video is there where he explained this initial part of your presentation.
Okay. So
I guess you're talking about the DALI.
Oh, sorry.
Yes.
I just get to let me share the screen again. I will need to show this. DALI is the a moment. I will need to share the screen on the Google. Just a moment. Yes. Okay. So this is not DALI, but I can give you the it's from OpenAI. They can creating their images from the text you imported, like armchair in the shape of avocado or something else. It's very interesting thing.
That's why they call it DALI. Because DALI was crazy. He was doing this type of images.
Yeah, and you can see they can generate different styles, not just in the same way. They can actually using, I think it's not, they have even the more advanced one, DALI 2. It can.
We have a
create-
Google Colab where you can actually test this also.
Yes, of course. You can actually using their code and well, like this, bowl of soup. You can see they have very different. Oh, this one is a little scary. So yeah, you can see it can generate from text to give you images of different styles. It's quite ridiculous stuff.
Any other questions for Qian?
Oh, by the way, the largest Chinese model is called Wu Dao, which is 1.75 trillion.
Trillion,
Oh,
yeah.
parameters.
See?
Yeah,
Yeah,
parameters.
Well,
Yeah, I knew there was trillion. Yeah, okay, yeah. From Chinese Academy of Science. Thanks, Lulu.
So thank you everyone for tuning in and for have a great weekend ahead.
Okay, bye-bye.
thank you.